My name is Ivan Pustogarov. I'm from the University of Luxembourg, and today I will be speaking about Bitcoin anonymity. When I was flying to this conference, I watched the movie Horrible Bosses 2, and Jamie Foxx was given a gun to three main characters, and he told that he bought this gun completely anonymously using Bitcoins. So I have an impression that people think that Bitcoin is anonymous. However, recent research disproves it, and even Bitcoin developers do not claim that Bitcoin is anonymous. This encourages people to use Tor. Why? One of the reasons is that Bitcoin does not encrypt its transactions. So everybody who is in between the user and the Bitcoin network can reveal the IP address of the user. It involves internet service providers or malicious peers to which the user was unlucky to connect, or if it can even be done with good enough probability by a remote low-resource attacker. So today I'll be speaking about issues which arise when a user decides to use Bitcoin over Tor. I will start with a brief background and motivation. I will then explain how to isolate a user from the rest of the Bitcoin network. Then I will describe a technique how to fingerprint or set a cookie on a user's computer. And finally, I will show two low-resource Sybil attacks. So what is Bitcoin? Initially, it was perceived as a P2P network. However, right now there is a core of Bitcoin servers which accept connections. And there are users which occasionally connect to this core network to send and receive transactions. And this is what we will be concerned about, the anonymity of transactions which Alice sends to Bob. So to increase the anonymity of the Bitcoin system, users are recommended to store and to generate as many Bitcoin pseudonyms, which are efficiently public keys. Right now, Bob is connected through Tor network, which is briefly a big set of proxies which Bob can chain and send his transactions through to the Bitcoin network. Usually, Bitcoin chooses three Tor relays, which are called guard, middle, and exit, and he sends the transaction, which travels all the path through the chains of relays and finally arrives to the Bitcoin network. So let's start with the first part, how to isolate the user from the rest of the Bitcoin network. The idea is very simple. There is built-in anti-DOS protection in Bitcoin, according to which if you're a Bitcoin peer and I send you a malformed message, you will increase the penalty score of my IP address. And if I send you malformed messages, you will increase and increase this score, and finally it will reach 100, which means you ban my IP address. So let's see what happens when an adversary tries to send a malformed message to the Bitcoin network over Tor. So he chooses a Tor relay, say R5, and he sends it to a chosen Bitcoin server. In this case, the Bitcoin server will see the malformed message coming from the IP address of R5. So Bitcoin server will effectively ban R5. Next, say the same day, Bob decides to connect to the same Bitcoin server over the same Tor relay R5. But he will not be able to do this because Bitcoin already banned R5. This implies a very simple strategy. The attacker just bans all good Tor exit relays, and he bans all good Bitcoin peers. Then he injects his own Bitcoin peers and his own Tor relays. This results in that when Bob tries to connect to the Bitcoin network over Tor, he will only be able to do this when he uses attacker's Tor relays or attacker's Bitcoin peers. So let's see how it looks like. For example, client 1 chose some good Tor relay. In this case, he will not be able to connect to a good Bitcoin peer because an attacker already banned this connection. So for client 1, the only option to connect to the Bitcoin network would be to choose a malicious Bitcoin peer. On the other hand, if client 2 connects to a malicious Tor exit node, there is no authentication in the Bitcoin protocol. So the malicious Tor exit node can impersonate whatever Bitcoin peer client 2 wanted to connect to. So what are the results? So the results are that an attacker can delay or drop blocks or transactions, which increases the probability for double spending attacks in Bitcoin. Also, an attacker can use classical traffic confirmation attacks to de-anonymize the user or reveal his guard nodes. And also during the very same session, since all the transactions go through attacker's nodes, he can link different Bitcoin pseudonyms of the same user. The problem is that when an attacker bans all good Tor relays and good Bitcoin peers, and a user will try to connect again and again, and if he chooses banned connections, banned Bitcoin peers, he might spend quite some time. And finally, he might decide that the whole system of Bitcoin over Tor doesn't work properly. So this graph shows a delay and how much Bitcoin peers and Tor exit capacity an attacker should have, which is reasonable. This is the first part. So what we have right now is that all the connections of clients who decided to use Bitcoin over Tor goes through attacker's nodes. Let's see how we can fingerprint those clients. And the idea, again, is very simple. And it is based on Bitcoin peer discovery protocol. There are just two rules which we should take into account, and they are rule 1. I can send you an address message to find out what IP address of other peers you know. And if I send sufficiently enough messages, you will tell me everything, all the IP addresses you know, which are stored in your database. And the rule 2, when I get a request to tell what IP addresses I know to another Bitcoin peer, I'm ready to tell everything. I'm ready to tell everything I know. And when I receive an address message back, I will store all addresses messages which are contained in this there, which includes any garbage IP addresses this address message can have. What it means? It means basically by sending addresses, I can fingerprint users or use it as an address cookie. And it will work. It doesn't matter if a client is connected to the Bitcoin network over Tor, VPN, or other proxy systems. And we can use different combinations of IP addresses for different clients. Let's see how it works. So we now isolated the client from the rest of the Bitcoin network. So whenever he sends a suspicious transaction, we also send him back an address cookie. Next, when he decides to connect to the Bitcoin network without Tor, just to send some benign transaction, we check this user for a cookie. And this allows us to reveal his IP address and effectively de-anonymize the user. There is one problem, is that for me as a Bitcoin peer, my database of IP addresses is limited, and I can store approximately 20,000 IP addresses. At the same time, excuse me. At the same time, whenever I make a connection to the Bitcoin network, I connect to 8 Bitcoin peers, and they will send me the IP addresses they know. So with each new session, with each new connection to the Bitcoin network, I will get about 20,000 non-unique IP addresses, which looks like every new session, within a couple of sessions, the fingerprint, which I already set, will be overwritten. However, actually, it is just an apparent problem, and in reality, the IP addresses which I receive will almost never overwrite the fingerprint, the cookie which I set before. And it is based on that first of all, me as a Bitcoin peer, I only store IP addresses about which I don't know. And our experiments show that about only 6% of IP addresses which I received are unique or new. And the second thing is that each IP address has a timestamp. And whenever I consider if I should store, whenever I decide to store an IP address, I need to replace it with some other. I need to put it into some slot which occupied by some other IP address. So how I do this? I just choose randomly 4 IP addresses which are already in my database, and I choose the oldest one. Again, our experiments show that for 45% of IP addresses in a client's database, they are older than 10 hours, which tells us that with a very high probability, the cookie set recently will not be overwritten. This table shows our experiments, and in a nutshell, within 10 sessions, we were able to preserve 36% of our fingerprint, which with very high probability allows us to uniquely de-anonymize the user. So the bottom line is that our fingerprinting technique survives restarts. It is preserved for many hours. And so, for example, within 24 hours, half of the fingerprint is preserved, which again allows us to de-anonymize the user. The bad thing for an attacker, this technique will be fixed soon. We also consent the fingerprint not only when a user connects through the Tor network, but we can also do this other way around. We can fingerprint the users when they connect to the Bitcoin network without Tor, and then when we see a suspicious transaction coming from the Tor network, we can request a cookie from the user, which means that we want all Bitcoin users to connect from time to time to our malicious peers. The problem is that right now I need one IP address per Bitcoin peer. I will describe 2 techniques right now. So the first technique is well known in the Bitcoin community, and it's also very simple. By default, a Bitcoin peer accepts 117 connections. This suggests a strategy: just get the whole list of Bitcoin peers and occupy the open connection slots. Then, whenever a client decides to connect to the network, he will not be able to connect to legitimate Bitcoin peers, so he will finally end up connecting to malicious peers. And we can update or set a new fingerprint to their computers. The second attack is based on the fact that if I already store an address of Bitcoin peer, I don't consider its port number when I decide to store it or not. So this suggests the following strategy. I broadcast in the Bitcoin network IP addresses of legitimate peers, but with the wrong port numbers. Then clients try to connect to those wrong port numbers, and which obviously fails. At the same time, when they receive an update of this IP address, they will not store those new IP addresses in the database because they already have the IP, but the ports number are different. So the wrong port number will stay in the database, and the client will not be able to connect to the network. So as in conclusion, we force all Bitcoin over Tor clients to connect through BIT, peers, or relays. We can set the fingerprint on their computers, which allows us to de-anonymize them. And we also know how to increase the chances that the client connects to malicious Bitcoin peers, so which allows us to refresh the fingerprint or request the known fingerprints from the Bitcoin clients. Yeah, this concludes my presentation. Thank you.
Thanks very much for that talk. I'll take the first question in the middle mic.
Hi. You don't mention any solutions for this attack. I mean, an obvious idea would be for one of the Bitcoin peers to
For which one?
For the first attack, where you get malicious exits to be blacklisted.
For banning Bitcoin over Tor.
For banning Bitcoin over Tor, right. So if some peers wanted to enable anonymous access via Tor, they could run a Tor hidden service. But then, I mean, they still have a DOS problem, right? Like a malicious peer
Sorry,
problem.
again? But
So if they ran a hidden service, then they could at least know this guy's coming over Tor, and they could apply some other mechanism other than IP banning. I don't know what that mechanism that would be. Do you have any suggestions?
So with hidden services, there is the first problem. Yeah, the first problem is that you can make a denial of service of Tor hidden services. This is first. Second, right now we checked it, and I don't remember the exact numbers. It's in the paper. Right now there are about only 30 hidden services to which a user can connect to the Bitcoin network. And the third problem is that for hidden services, Sybil attacks just work perfectly because you don't need additional IP address to run a Bitcoin peer. So you can run as many hidden services as you want. So my suggestion would be, if you know a hidden service which you can trust, you need to connect to that hidden service. And just choosing random hidden service will not solve this problem. So a hidden service should be trusted, you know. Yeah, so.
Thanks. Did you say that there are some Bitcoin peers who are running hidden services?
Sorry?
Are there some Bitcoin peers who are running hidden services? Is that what you said?
Easy.
Sorry. Are there some Bitcoin peers that are running Tor hidden services?
Yes, there are, like about 30.
Oh, I didn't know that.
So, and there is, on Bitcoin Wiki, there is a list. We found some others by making queries to the Bitcoin peers.
Cool,
Thanks. Can we take the question with the right mic?
I was going to ask really similar things to Aaron, but just to ask the other side of that, what would be, it seems like this hinges on the fact that Bitcoin's main denial of service prevention is banning IPs that do something bad.
Yeah.
So, I mean, it seems like a necessary alternative would be some alternative to that. So have you looked at any other ways that you would be able to prevent denial of service without just...
So I think the reason why they have Bitcoin anti-DOS protection is to prevent basically DOS in the whole network. So what can be done is that half of the network can, like with probability 1/2, your Bitcoin peer disables anti-DOS protection, and half of the network, like with probability 1/2, you still preserve this anti-DOS protection. So basically, this will result is that you cannot isolate all Bitcoin clients from the network. So but if by default you have 8 connections to the network, half of them will go through and half of them will choose a malicious peer.
Have you thought about anything like having clients have to pay in Bitcoin a peer that they're going to connect to for the open
Paying
slot?
with Bitcoins yes, I was thinking there is one paper which was presented at Financial Crypto actually about paying. but immediately I cannot think how it can help to solve this problem. I think it requires some more thinking. Yeah.
Thanks. We got one last question.
Okay, so what if we can modify the Tor network so that the Tor entry node will ban all the bad user who broadcast the bad message? So will that make a Bitcoin over Tor a good practice?
Oh, sorry. I'm sorry. I didn't understand.
So what if we modify the Tor network so that the guard node we check if an user is broadcasting a bad message, so that the guard node we ban the
guard
bad
node?
user? Yes.
The guard node rejects
Yes.
what? Rejects what?
The guard node we ban the bad user so that the Tor exist node will still work.
Sorry. The guard node is the first node in the Bitcoin chain.
In the Tor network.
Yeah.
Yep.
So what?
So
The guard node cannot do anything because he
So-
just sees an encryption. He sees an encryption connection, so he cannot distinguish if it is.
I am saying that what if we can modify the Tor network so that the guard node can ban the bad user, right? So will that make Bitcoin over Tor a good practice?
I think it's a really good question for the Tor
Yeah,
developer
probably.
community.
It's the fundamental motivation of Tor.
I see.
Well, there you have
Yeah.
it.
Okay. Thank you.
All right.
But we can discuss it offline. But
Okay, sure.
Yeah, let's thank the speaker one more time.